Hi, this is Lauren Ostergren. I'm the product manager for the Nova software. On behalf of the Vassal team, I'd like to give you a short demonstration of the Nova software. Nova, non-invasive optimal vessel analysis, is our method to quantify blood flow using magnetic resonance imaging. The test is called quantitative magnetic resonance angiography because it combines the visualization of MRA with quantitative hemodynamics in the individual vessels. I have Nova running on my laptop here, so we can switch right over to the Nova application. Now, Nova is performed in real time while the patient is in the scanner. The Nova computer is in the MR suite on the network, and it can receive images from the MR scanner. So we're going to walk through the workflow as if this were a real-time Nova study. We start with the institution's standard 3D time-of-flight MRA. After that sequence is completed, they will push it over to the Nova workstation, and it'll transfer over the network and appear here in process. So all I need to do is select that study and load the time-of-flight MRA images. Now there are two parts to Nova, 3D model and 3D flow. We're going to start in 3D model. Here's our time-of-flight sequence. Nova automatically identifies it as a head and neck sequence, so we'll create new. Now we're walking through a study. This is a study that was part of our baseline study of the normal population to establish normal ranges. So when the time of flight comes over, it's going to load the MRA, as you see here. And the first thing I'm going to do is crop the MIP in 3 planes. So I just take my mouse, left click and drag, and crop. And now finally, we'll do this in coronal plane and crop. And this typically takes about 30 seconds or less to generate a 3D surface rendering of the blood vessels. So now I've clicked T. Nova automatically thresholds the signal, and then all I need to do is click 3D, and I have my 3D model. Nova's algorithms automatically highlight cylindrical structures, vascular structures in yellow, so I have a quick and easy way to filter out any signal due to noise by selecting yellow only. So here's my 3D model. Again, it takes about 30 seconds. And I think what we'd like to demonstrate for you today is the Veritas protocol. That is the protocol for vertebrobasilar disease, which will risk stratify patients according to their flow status. There are 3 measurements taken for the algorithm. The basilar artery. So I'm going to select that with a left click, label it with a right click, and then bilateral PCAs. Here's the left PCA. Just click with my mouse and select the appropriate label from the drop-down menu, and right PCA. And notice Nova has automatically oriented that perpendicular, and the algorithms determine the center scan line, so I can actually walk this cup up and down the vessel segment and maintain that perpendicularity. So red axis is the patient's right, just a right click now to label that. So you can see that took not more than a minute or 2, and I can then transfer these coordinates to the scanner. Now I'll get an error here because I don't have a scanner in my office, and again we're just simulating how it would be in the real time setting. So those coordinates have been sent to the scanner. This technologist can pull them from the network. The protocol parameters are already set up on the scanner like any other protocol, so they can begin to scan those immediately. They take about 30 seconds to run, so I can now switch over to 3D Flow, the other part of Nova, and start to look at the results. So a 3-vessel scan like a Veritas protocol will be less than 5 minutes additional time. Nova gives the option to measure as many vessels of interest as the physician would like to see. The The additional time is going to be proportional to the number of vessels studied. If 5 or 7 vessels are requested, that's going to add about 5 minutes to the protocol, and so on. Okay, so here are measurements that have come back. Now, this was a full protocol. All of the vessels in the head and neck were studied. We're particularly interested, though, in the posterior vessels in the Veritas algorithm, so we're going to jump right down to the basilar artery. And you notice all of the vessels have standard labels. These are very standard in neurosurgery for labeling the circle of Willis and the major cerebral vessels. So we follow that terminology. So I've selected basilar artery. At the top, we have an inset of our 3D model. And at the bottom of the screen, we have the phase contrast MR images that were obtained at this level. So using the NOVA 3D model, I selected my location for measurement, and we scanned at this level. And here are the images that come back to me from the scanner with the flow already calculated. All of the processing in NOVA is automatic. So what I'm going to do here is just a quick quality check to make sure that these images meet my criteria for an accurate measurement. And there are 2 main criteria when you're performing flow quantification with MR. Your 2D scan plane needs to be perpendicular to the vessel, and our algorithms guide that selection and ensure that that orientation is perpendicular. And then the second criterion is laminar flow. So as you'll see in the next screen, we have available velocity contours. This is a cross-section of the artery showing the distribution of velocities in the lumen of the vessel. The highest velocity, maximum velocity, is red, and then these other colors represent diminishing velocities until you get out to the vessel wall where it's stationary tissue. The velocities are calibrated according to the scale you see on the right-hand side of your screen. The great thing about this is that at a glance you can visually confirm that you've got laminar flow. These concentric rings show that we have the peak velocity in the center, and then the velocities decreasing as we get out to vessel wall. So thus confirming we have laminar flow, a requirement in order to know that these measurements are valid and accurate. At the bottom of the screen, we also show the flow waveform. We've got a volumetric flow waveform where the units are milliliters per minute. We've measured at various points during the cardiac cycle to generate this waveform. And on the right-hand side, we have a velocity waveform, which will have a similar shape to the volume flow. The next screen is where I can take a snapshot, a picture that I want to go on the report. So I'll just save that image, and I'm done. So as you see, the processing is automatic. The report is automatically generated. So I am simply doing a quality check to make sure the patient hasn't moved and my images meet my criteria for an accurate measurement: perpendicular orientation of my scan and laminar flow. So let's run through that one more time. On the left PCA, this is the vessel in the Veritas algorithm. So again, I'm going to quickly do a quality check visually here. I see that my region of interest box is centered on my vessel. Now I could move that if I needed to. And that the scan plane is on the left PCA. Again, these images are co-registered. The 3D model comes from the time of flight, and the bottom images are the 2D PCMR images, which give us the flow quantification. So that looks good. Here are my contours. At a glance, I can confirm laminar flow. I have a nice smooth waveform. And finally, the picture I'm going to send over to PACS. Okay, so we are all done. I can go ahead and submit the study. NOVA will remind me to do a VENC check. VENC, velocity encoding, is one of the parameters of the MR scan that optimizes the sequence to the flow to be measured. NOVA has a way to automatically check and make sure that the velocity encoding parameter is optimal for the flow to be measured. And that's all, again, automated. So here's my report. I've got a schematic map summarizing all of the vessels, a baseline table with the individual flows measured in the study, and age-adjusted normal ranges for reference, and then a flow summary page. Every measurement has a snapshot of the 3D model and the waveform. Now I'm going to go ahead and submit that report. It can go over to PACS from here and be viewed by the requesting physician. It can be printed. And we can browse it. So let's go ahead and now browse this completed study. So we're going to load up all of our images. Here's the report again, the vessel map. We'll take a closer look at this now. This is an annotated schematic cartoon, if you will, of the arteries of the head and neck, the flow rates in milliliters per minute, and the flow direction are indicated. All of these red segments correspond to a measurement that was taken in the study. And at the top of the page, you see we also calculate the total cranial flow. That's the total flow going into the head. And that can be a useful index for the individual flows. I can click on the 3D tab and show you just how easy it is to maneuver this 3D model. And what beautiful resolution we have of the entire vasculature. NOVA protocols are optimized to measure blood vessels down to 1 millimeter in diameter, like these PCOMs you see here. And let's move ahead to our baseline table. The individual vessels are listed in the first column and the respective flows in milliliters per minute. And if this were a patient, the patient's age range would be in bold for easy reference for the clinician. And again, our flow summary page. And I can quick jump to any particular measurement and all of its associated images just by clicking that vessel on the list. So here is our basilar artery with the waveform. I'm going to go back to the 3D for a moment so I can show you something NOVA has. It's very exceptional. This is 4D flow, what we call 4D flow, adding the temporal resolution, adding the dimension of time. And I can look at the selected vessel just by itself. And this is the actual flow, animated. Now this is not a simulation. This is the actual flow we recorded with the retrospectively gated sequence. So we can see the laminar flow in the basilar artery very clearly. We can also see the flow in the vessel wall. So here we have the flow in the lumen of the vessel, obviously true laminar flow. And then at the edge here, at the border of the vessel wall, we can appreciate the vascular response in the vessel wall itself. So you see we have actually sort of a W-shaped waveform here, where we're picking up flow in the vessel wall, which would potentially be very useful with this kind of time resolution, or even higher time resolution, to look at vessel wall distensibility. Now that's the basilar artery. We can take a look at another example of 4D here. So here's the left internal carotid artery. I'm going to select just the carotid here, animate it, look at just the vessel. Now in this plane you can see we're actually showing the venous flow as well. There's the vessel wall, laminar flow in the internal carotid artery, and then the venous flow, which is occurring predominantly during diastole. So really quite fascinating and detailed analysis of the flow profile that's available. Okay. I'd also like to show you the additional information that's available in browse mode here. So previously we were conducting the study. I showed you how the processing is completely automated. Now we're viewing a completed study, and all of those source images are still available to us. I can view the time of flight. We have a built-in 2D viewer. So this is available for quick reference. I can look at all of the source images, PCMR and contours. So here are the velocity contours for the basilar artery. And again, these are perfect, showing laminar flow. And I can also click on the PCMR tab to view the 2D PCMR images and see how clean and noise-free these are and how distinct the vessel is in the center of the image. And finally, we can also quick tab to the waveforms for the basilar artery. You notice I have the flow rate tab selected here, but we also have the ability to look at the area and the diameter of the vessel. And we can look at velocity in terms of the peak velocity at each point in the cardiac cycle, or the average velocity at each point in the cardiac cycle. So this is a quick tour of the NOVA report. We've looked at a Veritas protocol and the 3 measurements that would be taken in that study that's less than 5 minutes. And this study is about to be published, but it's an algorithm that would apply to, in the US, about 200,000 posterior stroke patients each year that would benefit from this 5-minute study. Now I'd like to move over to a PowerPoint and show you some of the additional features in NOVA. We'd like to switch back to PowerPoint now and close with a few slides to show the range of applications for NOVA and some of the specific enhancements we have built into the software for these applications. And in the demonstration today, we emphasized the Veritas protocol. This is a 3-vessel protocol that can be done in under 5 minutes, and it provides information on the flow status, which the physician can use to guide treatment decisions. Patients with normal flow have a relatively low risk of stroke and can be managed conservatively, while the patients with low distal flow have nearly 6 times greater risk of stroke and can be offered interventions to mitigate that risk. So for example, at University of Illinois, they will immediately consider an intervention for a patient that's found to have low distal flow based on the NovaQ MRA measurements and application of the Veritas algorithm. They will immediately consider intervention for these patients. Another very interesting area for neurosurgeons is intracranial stenting. And even though we have a signal void here from the metallic artifact, it does not affect the ability to quantify blood flow in the distal vessel. So NOVA will provide that measurement and not be affected by that artifact. One of the features we have in the NOVA report is the comparative map. You'll see here two measurements. This is before and after angioplasty and stenting. So the neurosurgeon can see how much flow has improved after an intervention, and this is all summarized, the two studies side by side on the same map, and this is also information available to them on the PACS system. We have a specialized map for ECIC bypass that adds the additional labels, annotation, and schematic for an intracranial bypass. Those are performed for Moya-Moya disease, as well as flow replacement to manage giant aneurysms. Another application that we're seeing increasing interest from among the neurosurgeons is the capability to quantify cerebral venous flow. This is important in guiding treatment strategy where a patient will be undergoing a series of embolizations. The neurosurgeon can check the flow after each procedure and then time the surgical resection with the appropriate reduction in blood flow to the AVM. So we have a specific cerebral venous map to depict those measurements. NOVA has the capability to measure cerebral spinal fluid flow as well as blood flow. And we've done pilot studies in volunteers to show the feasibility of this, where we can put the measurement plane on the cerebral aqueduct and actually quantify the CSF flow. Small arteries, such as the digital arteries in the hand, can be measured. We've optimized the protocols for these tiny vessels, and this work has already been presented at one of the Magnetic Resonance Society meetings, the ISMRM. Hepatic artery and portal vein, the renal artery, and also the lower extremity arteries are all possible using the same software interface. We have simply tailored the protocol and provided an application-specific map. This gives a range of the applications that are possible with NOVA using the same software and choosing the specific application of interest, but the basic technique and the operations and navigation of the software that the technologists will have learned will transfer over to any of these applications. So I'd like to close by thanking you for your time and your consideration of how important it is to the neurosurgeon and to his patients to know the flow.